Hi, I'm Rich with insideHPC. We're here at ISC 2015 in Frankfurt, Germany, and we're here at the Allinea booth with Mark O'Connor. Mark, how you doing today?
Hey, I'm doing great. Rich, how are you?
Well, great to see you again.
Yeah,
you know, I've heard some new things about Allinea Map. Are you doing a demo today?
Sure, I got a couple of cool things to show you today.
All right.
So normally on these sessions we like to do an intro to the products and show how they work for some simple examples. Today I'm not going to do that at all. I'm going to look at real-world codes and real-world problems that we've been seeing with our customers and users over the last few weeks and months, just to show some interesting insights that we've had. So here's one, just to kick off. This is Performance Reports, for those who don't know. This is one of our three kind of main products. We have Forge, that does development tools, debugging and profiling, DDT and map. And we have Allinea Performance Reports that does analytics and performance tuning. So this is what you get out of Performance Reports when you run it on an unmodified binary. It just dumps out this HTML page, gives you a nice summary of how the run went. What it is Hydra, it's real world code. We are running this on our internal cluster, and we found some really interesting things out that I'd like to show you. So when we look at this code, the first thing we see is it's spending 84% of its time compute. That's very good. That's what you expect. But this is only running with 2 processors and a single node. So we scale that up to 16 processors, screen 2, and wow, that drops straight down to 20%. That's huge. That's all the time now spent in MPI and in I/O, which is really not what you want. So we can scroll down here. We have these different breakdowns of time in CPU, in MPI and in I/O here. We see in the I/O time particularly, we're spending all of that time in writes, with a write rate of 1.38 megabytes per second. That is awful for HPC system. So we ran map on this to see what was going on. So here's map on the 2-process single node version. Here we have the horizontal axis or time from the start of the job to the end. Green is time spent computing in OpenMP. Blue is MPI, and orange is I/O. So we can see here this is all super happy, and when we look at the 16-process version on 2 nodes, wow! So it's all blue, that's tons of MPI. In particular the I/O, we can see it gets more and more I/O intensive towards the end of the job. We can actually zoom in here and have a look at this. And when you zoom right in, you can see the individual iterations of I/O going on there. Now, map lets us dig in and say, where's that I/O coming from? And because map, unlike other profilers, it samples across the wall clock time and not just what the CPU is doing, it shows where you're waiting as well. In particular, we're waiting here in this fopen function. And that's kind of strange. You wouldn't expect to spend 18% of your time waiting in fopen normally. And if we look a little bit higher up here, you can see what this code is doing is it's creating a new file with every single process, every single time step. And every time the parallel file system has to deal with that, it has to synchronize to make sure nobody else is making the same file with the same file name. That's a locked operation, which is hugely inefficient as you increase the number of processes and number of nodes. You're really just DDoSing the file system at that point in time, which is why this is performing so poorly. So we ran this again using the local file system, and in fact we looked at all the memory usage here. It's only 33 megabytes, that's nothing. So we actually wrote to the shared memory file system, which is much, much faster, and then copied the data in one go at the end of the job instead of hammering the file system in parallel during the job. And when we did that, we see immediately, bam, the I/O time just disappears, and the total runtime drops to just over a minute long. So we have made this job more than twice as fast. If you look at the full scale, zoom back out, this job was running for 164 seconds. We've lost 100 seconds of runtime over half of it, just by learning that we need to run on the right file system. And this is a real change that will benefit people in HPC. I also want to show you how this looks when we bring up the performance reports. So you think, okay, great, I've got a 2 times speed up, that's a great win. And when we see that in the performance report here, bam, yeah, the I/O time's dropped to 0, almost 0%, and the write rate's now at 57 megs a second, that's much healthier. But now we're still spending all of our time in MPI, particularly here, 90% of the time in collective calls, which are really just blocking waiting for the processor. So there's still a lot of work to do on this code. And then you move on to the next stage, and it really helps people also, not just the HPC professionals who, in the support teams have to do the kind of thing as their bread and butter, but the scientists who don't know they have a problem until they see a report that says, boom, you've just sacrificed all of your compute time. It makes it really visually obvious and brings a culture of performance awareness to the whole site.